I'm gonna first introduce you. Yeah. Hello, everybody. Welcome to Tiedekulma, the next frontier in fundamental physics. We are here celebrating, among other things, the 30th anniversary of the Helsinki Institute of Physics. My name is Isak Rauto. It is my pleasure to have the honor of hosting this event for all of you, especially here in beautiful Tiedekulma, a place that I have spent many an hour in studying, both deeply focusing and letting my mind wander. Both of those is what discovery is all about. Even this room itself kind of symbolizes that for me in some ways. Like, if you know where to look, you can see the shimmering light of a new world of knowledge somewhere. I don't know if that's what the architect intended, but it sounds very good in my intro. So that's all that matters. We are, as I said, here celebrating the 30th-year anniversary of the Helsinki Institute of Physics. And at this moment, I'm curious about you, the crowd. Who here is a physicist or somehow involved in physics? Perhaps knowing. Great. Most of you. Who here is not a physicist? Who here has no idea where they are right now? There's a few people who have no clue where they are. Nice. By the way, I am like you. I'm here for everyone, obviously, as a moderator, but for you non-physicists, I'm like you. So we're all surrounded by all these smart mathematical geniuses here. Don't worry, you are not alone. I am here with you. So, a little bit of information for both you who are aware of what this is all about and those of you who aren't. The Helsinki Institute of Physics is a joint research institute founded in 1996. I know you already had that number in mind, good at math. They consist of the University of Helsinki, Aalto University, University of Jyväskylä, Lappeenranta University of Technology, and Tampere University of Technology, as well as, and actually this is not in your English Wikipedia page, so someone might want to go and fix this, but the Radiation and Nuclear Safety Authority, Säteilyturvakeskus, is apparently also part of HIP. Very interesting. They are, as I said, founded in 1996. They do research on basic and applied physics, as well as on technology development in international accelerator laboratories, one of which is very well represented here today. They're also very proud of their mission of social impact and researcher education, and I happen to personally know, having interviewed one of them, Alexi, that they have some very sharp people over there at HIP. There's also a very interesting connection between the aforementioned research institution CERN and HIP, ever since Finland joined CERN in 1991. Seeing the year 1991 here, I imagine that year is not completely coincidental. Put it this way, I'm assuming there were a lot of Finnish physicists in 1991 who were very happy that Finland could finally join CERN in 1991. And ever since HIP was founded in 1906, they have been responsible for the collaboration between Finland and CERN. So that's pretty cool. Anyway, we don't really have that long of a program here today, so we should shortly start proceeding. We will have two sets here, two segments in this evening's program today. The last one will be a panel discussion about the future frontiers of particle physics, and we'll have 6 very distinguished, very intelligent panelists here discussing those topics with me. But before that, we will have a presentation by none other than the Director General of CERN himself, Mr. Mark Thomson, sits right here. And after both of these segments, you audience, if there's time left, you will have the opportunity to ask questions. So listen with that in mind. I actually don't know how we'll handle the practicalities, but I'm sure the sound guys over there will give you a microphone, or then it's a pretty small room. Maybe we can hear you if you just produce enough voice for us to be able to hear you. But anyway, without further ado, let's proceed with the program. I wish you all welcome here to Tiedekulma. Let's celebrate the 30th anniversary of the Helsinki Institute of Physics, international collaboration, the joy and awe of discovery and science. Mr. Mark Thomson.
Thank you. It's great to be back in Helsinki. It's not the first time I've been here. Beautiful city, the sun always shines, apart from today. So I'm going to talk a bit about particle physics. It's a rather personal view on where we are in particle physics, where we're going, what's important. It's a public lecture, so even for the non-physicists in the audience, or the physicist deniers in the audience, you should be able to follow everything. So it's personal perspective, where we are today, talk a bit about the next 10 years, which actually is why there are so many particle physicists in Helsinki this week, in fact, going beyond 10 years, and then then what? Obviously, I'm going to give a strong focus on CERN, tell you what CERN is, tell you what our big colliders do, what the challenges are. Always good to look back. I'm a scientist, very interested in the history of science. Just thinking about what's happened in the last 30 years in science, we've actually made huge progress. And I picked out just a few big discoveries. This is in particle physics and associated fields like cosmology. In 1995, we discovered a particle called the top quark, incredibly heavy, surprisingly heavy. That was a big, big surprise. Back in 1998, we thought these particles called neutrinos, they're everywhere, whizzing through the sky, doing not very much. We thought they were massless. We now know that was not correct. Something called dark energy was discovered in 1998. I'll come to that a bit later. Then rediscovered. A really big one here, we discovered something called the Higgs boson at CERN in 2012, one of the biggest discoveries in science, probably in the last 50 years. And actually, not that long ago, things called gravitational waves, these are now tools for looking at the universe, hadn't been observed. So these are big, profound discoveries. Every 5 to 10 years, we make a very, very large discovery in either particle physics or cosmology or astrophysics that changes our view of the world. So that's pretty impressive progress. So, we're waiting for the next one now, obviously. So how do we explore the universe? That's effectively our job. This graphic I like very much. This is the history of time, history of space, starting with the Big Bang, coming out to today. And what we want to try and do as fundamental scientists, fundamental physics scientists, we really want to understand how to use this pointer. We want to understand the history of the universe from that point up until what we see today. So right from the Big Bang, the beginning of time, to the stars, the black holes, everything we see out in the universe today. So that's 13.8 billion years of history. We do that in two ways. We like to look back in time, and yes, you can look back in time. With telescopes, we peer through the universe, and the deeper you go in the universe, you're actually looking at the universe earlier on in time. So we can do that up to about 1 billion years after the Big Bang. There was then this period, which you see, no stars. This is called the cosmic dark ages. Nothing much was happening then. And then there's a point where you can't see beyond. And this is because the universe was so dense, light just doesn't get out. Now, we want to know what happened really early in the universe, so we can't use telescopes. So what we have to do to get beyond this 380,000 years is we have to recreate the conditions that existed a tiny instant, and it really is a tiny instant after the Big Bang. That's what we do with our accelerators. That's what we do at CERN. I didn't check whether we were doing that today. I look at my colleague, my director of research, he's nodding. We are recreating the very early conditions, not the very earliest, but the very early conditions of the universe at CERN, right today, right now. So that's what we try and do. We try and map out the history of the universe. So fundamental physics, we aim to understand the universe from the Big Bang to the stars, galaxies we see today. The questions we're interested in, there's a few of them here. What are the building blocks of the universe? How does the universe actually work? How does everything come together? That's the forces. And then how did the universe evolve? So how did we get to the structure we see in the universe today? So that's things like black holes, stars, galaxies, and the role of this mysterious dark matter, which I'll touch on shortly. So that's our mission. This is a really simplistic view of matter, but it's actually an amazing one. That the stuff that you see in this room, you as well, you're made of matter. Inside you're built up of atoms. They're the basic building blocks of macroscopic matter. Atoms have electrons orbiting a central nucleus. Electrons are fundamental particles. We believe they are basic building blocks of the universe. If you go into the nucleus, you find there are protons and neutrons. If you look inside the protons and neutrons, we know there are things called quarks. So everything in this room is made of electrons, up quarks, and down quarks. That's quite remarkable. All of this complexity you see in front of you comes from just 3 particles. Not slight pushing the point, but it's very, very close to the truth. There is another particle that this room is full of them, buzzing through you. They're passing through you all the time. They don't do anything, though, or very rarely, and they're called neutrinos. So there are kind of 4 basic building blocks of the universe. 3 of them make up all the matter you see in here. So that is an incredibly simple picture. That's an amazing picture, very simplistic. The reality is a little bit more complex than that, but not much more. So I always find it remarkable that we've managed to get to a point where we can describe pretty much everything we see in terms of very, very few basic building blocks of the universe. We don't just want to know what the universe is made up of. We actually want to understand why the universe is the way it is. And that's a much, much harder question. So how do we answer questions like this? We build big machines, and this is really where CERN comes in. And I'll try and use the next few minutes trying to explain what CERN is, what we do at CERN, obviously why it's so exciting. Firstly, CERN is the world's biggest, most powerful particle physics lab, by far. It sits at the heart of Europe, on the French-Swiss border. It is our laboratory. As Europeans, it is our particle physics laboratory, but it is the most powerful in the world. As I say, it sits on the Swiss-French, I was going to say French, the Swiss-French border. That's that line there. To put it in scale, that's Geneva Airport. This is where our main site is here. And this big ring here is the outline of our largest collider, the Large Hadron Collider. We have a really simple mission at CERN, and our mission is simple. It's to understand the most fundamental particles and laws of the universe. Really simple, very clean. It's a very nice mission to have. It's very hard to do, of course, but we do our best. The other thing I think is really important, it's built on 70 years of international collaboration. The reason CERN has been so successful is that international collaboration, primarily European international collaboration. I'll say a few words about that. But again, it's something we should be proud of in Europe. Just to give you a sense of scale, CERN was founded in 1954. This was in the post-war period, where obviously there was a sense of trying to bring science back to the UK. There had been a big brain drain to the US. And CERN, one of the concepts of CERN was to actually try and reverse that brain drain. But also the idea that you start using science for peace, really to bring countries together in the fragmented Europe after the Second World War. We have 25 member states, including Finland, as you heard earlier, 11 associate member states, some of which are outside Europe, and 4 observers who play an important role in CERN, but they're not actually members. Give you a sense of the budget of CERN is 1.2 billion Swiss francs, or 1,200 million Swiss francs. That sounds like a large number. It's about the budget of a mid-scale university in Europe. So it's a large budget, but it's not incredibly large. We have at CERN 2,700 staff, 1,200 graduates and fellows, but the important people, the really important people, are the 14,000 users, the scientific community that comes to CERN to use the facilities. Now, of course, what our staff at CERN do, they're incredible people. They're mostly engineers, technicians, applied scientists, and they build this most incredible infrastructure, which is world unique. So we're primarily an engineering laboratory that provides the physics facilities, the best top-end physics facilities for the global physics community. So that's what we do. So we're a technology organization, but technology for science. We push the boundaries of technology in a number of ways. So we obviously cover some core technology areas. We build accelerators. That's pretty obvious. We build giant detectors. This is a picture of one of the detectors at CERN. You don't get a sense of scale here. This is like a 4-story high building. These detectors are huge, complex systems, and I'll say something about those shortly. And we rely on very advanced computing and have done for many years. The World Wide Web, as you are probably aware, was developed at CERN when I was somewhat younger, when I was a postdoctoral student back in the 1990s. And we were playing around with this new tool for sharing data and sharing information, having fun with it. But it's obviously had quite a big impact on society, largely positive. The jewel in the crown at CERN is the thing we call the Large Hadron Collider. This is just a picture. These blue objects, these are superconducting magnets that steer particles around this very, very large ring that I'm going to talk about at the moment. Very, very advanced technology. It is the most powerful tool we have to explore the universe. It's large, 27 kilometers in circumference, so that's that circle there. It collides hadrons, so we accelerate hadrons. These are typically protons, and we accelerate protons to 99.999991, and I added too many nines. I often do that. Very fast, almost the speed of light, because what we want to do is get as much energy in our protons as we can, smash them together to recreate those conditions we had just after the Big Bang. And we collide those protons. We don't just send them around the ring for no reason, but we collide them 40 million times a second. So inside our detectors, things are happening 40 million times a second. So they're going like that, but much, much faster. And we photograph, we image photograph what comes out. This machine is incredible. It's the most powerful collider ever built. It's an incredible feat of engineering. To make this machine work, my colleagues at CERN, they're just brilliant. I mean, this is not simple. This is not small-scale engineering. It's large. It's superconducting. 27 kilometers of superconducting magnets. If you get something slightly wrong, you lose the beam. That's a very bad thing. And we have to accelerate these protons to near the speed of light and send them around a 27-kilometer ring very, very precisely. We collide those protons, as I say, 40 million times a second. One of the statistics I think is really interesting, the energy of these protons going around the ring, and these are particles, small particles, is about 350 megajoules. Probably that number doesn't mean very much to you. Equivalent to just imagine here on the stage, there are now 1,000 stampeding African elephants running towards you. That's not a good thing, by the way. But that's the energy we have in the Large Hadron Collider. It's a huge amount of energy. Or it's equivalent to the energy of an A350 as it lands. But these are just small particles whizzing around a ring close to the speed of light. Or it's enough to melt tons of copper. So we have to control that beam, because if we don't control that beam, we burn very, very large holes in our accelerator, and that would not be a good thing. And that's really where the super precision engineering comes in. It's not just about accelerating the particles, it's about controlling things very, very precisely. It's incredible. It's just an incredible, beautiful, beautiful machine. So what we do is we have about 2,500 bunches of protons going one way around the ring, and 2,500 bunches of protons going the other way around the ring, and we bring them together at 4 points where we put these giant detectors. Being physicists, we like giving them obscure names, Atlas. Although I've given a talk like this probably 100 times, I always forget what Atlas stands for. It's an acronym that's very contrived. A large toroidal apparatus for what was? Oh yes, that's it. A large toroidal apparatus. Yeah, great. Anyway, very contrived. Very, very large detectors. It's the biggest detector. The CMS detector, compact muon solenoid, says it's compact, it's huge. ALICE, special detector, and then another one which does actually make more sense. But what we do at these 4 points is we bring these bunches of protons together, smash them together, recreating the conditions that existed a tiny fraction after the start of the universe. And these detectors produce very large, very complex images. They're the size of big buildings. yeah, actually this hall is actually not a bad way of visualizing the scale of the Atlas detector. Atlas is a bit bigger than this, but that's how big these detectors are. And in these detector volumes, we try and image all of the particles that come out of these collisions. So we smash things together, create lots of energy, and then stuff comes out. And that's what you see in this kind of image here. So they're three-dimensional cameras operating at 40 million frames per second. Really impressive. Just to give you some sense of how difficult these detector systems are. And of course, I should just emphasize, these detector systems are built by collaborations of universities around the world. So even the way we put these detectors together is quite a remarkable achievement. So we have 40 million collisions a second. So it's a very, very high event rate. We actually get over 1 billion proton-proton interactions per second. But we're interested in the really rare things that happen. It's not the things that happen all the time. That's interesting as well. But the really interesting things, like Higgs bosons being produced, happen very, very rarely. So what we have to do is sift through all of this data and find these very rare events. And that's why these detectors are so big, so precise, so we can actually measure in detail and identify the rare events. Try and bring that to life. This is an event picture that just gives you a sense of what the events look like. Protons come in on one side, inside this little pipe, and protons come along the other way, along this pipe, and they smash together at the middle of this detector. All of that energy, and it's a lot of energy, is converted into particles. Maybe we produce a really massive particle, and then it decays into many, many other particles. So we see sprays of particles coming out, and we measure the properties of those particles very, very precisely. So this is why you can interpret these images in computers. They look like three-dimensional images of exactly what's going on. The remarkable thing about this is you can look at these images, if you've got a train, if you understand how, we get our computers to do it for us, but you can actually figure out from this image, probably, what quantum mechanical process happened when those two protons collided. That's pretty remarkable. And so you're looking at the quantum world with detectors the size of this building. Impressive. Lots of data. I won't say so much about the data. We produce a lot of data. I want to say a bit about the Higgs boson and why it's so special. This is our thing we call the standard model. This is our... Oh, somebody has a T-shirt. Excellent. This is the thing we call the standard model. This is basically putting together all of our theoretical concepts into one equation, one model. It's a really strange construction. It has deep theoretical concepts, special relativity from Einstein, quantum mechanics from, well, many people. Paul Dirac put this together to make a relativistic theory of quantum mechanics and realized you had to have spin, particles had to have spin, or fermions had to have spin, and antimatter had to be there. Feynman and many others then turned this theory into what we call a quantum field theory, where particles are excitations of fields. And then in the 60s, there was a big revolution on trying to realizing that you could actually understand what all the forces are in the terms of a very interesting symmetry principle called the local gauge symmetry principle. And then all of the forces drop out of that, in some way anyway. And then at the end, you add the Brout-Englert-Higgs mechanism. I'll say more about that in a minute. But that's not enough. You have to mix that in with what you actually see. So all of these ideas, they're theoretical concepts. They don't tell you what the masses of the particles are. They don't tell you how many particles there should be. They don't tell you how many things, we'll come to that in a minute, generations there are. They don't actually tell you some of the, they predict how the forces should work, but they don't exactly tell you what types of forces you should have. So you have to put that all in by hand. So you've got theory, and then you mix in the experiments. I think the experiments is the kind of egg in this picture. It's the gooey stuff. Mix all that up together, and then you come out with what we call the standard model. And we put that on the T-shirt and sell it in the CERN gift shop and online. So it's an interesting construct. The Higgs boson is absolutely key to this, and I'll try and explain why it's so different. This is our standard model here. These are the particles. I already mentioned the up-down quark, the electron, and one neutrino. That's the basic stuff in the universe. That's what makes up what you have mostly in this room. We've discovered in our colliders that you don't just have an electron, you have a heavier electron and an even heavier one. So you get a copy of the electron and another copy. We don't know why, but we know they're there. So we actually have 12 particles of matter, and then we have some particles that make the forces work. So not many particles, but it's really strange because, as far as we know, these particles have no size. They're pinpricks in space-time, or maybe strings in space-time, but the miracle, the really strange thing about this standard model is it doesn't work for massive particles. The whole thing only works for massless particles. So particles do not have mass in many senses. But that's counterintuitive. I mean, we think we have mass, sometimes too much after those cinnamon buns. So particles do have mass. So something's wrong here. And the miracle that makes the whole thing work is the Higgs boson, or actually more specifically, the Higgs field. So this is the particle that gives everything in the universe mass, as far as we know. So if the Higgs field was not there, or if it didn't have a very strange property, all of your particles would have no mass. They'd all fly off at the speed of light. That would be very, very unfortunate. Fortunately, the Higgs field is there. So how does this work? This is I do know there are some there's an eminent theorist at least one eminent theorist in the room, so I would ask Michelangelo not to listen. This is my analogy. The Higgs field is in some ways a property, or you can think of it as a property of the vacuum. So if I go to the furthest depths of the universe, it's still there. And that's very, very unusual. All of the other particles, they're not there, there's nothing there. But in some sense, the Higgs field is always there. Really strange property. So this is my analogy. This is a very physical analogy. The Higgs field somehow makes the vacuum, nothing, a bit sticky. So it feels a bit gooey, muddy. So just imagine this field of mud here. Now, if you're a massless particle, if I run across this stage, I can run really fast. Actually, I can't run really fast, but I could run reasonably fast across this stage, maybe at the speed of light or close to the speed of light. But if I then filled this room with a field of mud, I'm not going to be running very fast. It's going to be very hard for me to accelerate, because I'm now not traveling through a vacuum, I'm traveling through a field of mud. So what that would do to me as a massless person, it gives me something that feels like mass. It's really hard for me to move and accelerate. And that's kind of how the Higgs field works. All particles feel the presence of the Higgs field as they move through the vacuum. And that gives them something that looks like mass. In some sense, they're not. They're just feeling the Higgs field. Now, what we do at CERN is we take... Oh, there's our people walking through the field. This is a field of mud in Gloucestershire. It's in the west of England. It's a place where they do strange things like rolling cheese down a very, very big hill and running after it. And I think 10% of the people who do that break limbs. It's a very steep hill. They also have races crawling through the fields of mud. So Finland is actually a very civilized, and I understand why, Finland is the happiest place in the world. In Gloucestershire, they do strange things. But what we do is we take that field of mud, the Higgs field, and we hit it really hard with our protons colliding, and you see ripples coming out of that Higgs field. Those are the particles we detect, the Higgs bosons we detect. A few words about the LHC. The LHC is a beautiful machine. This is my only physics plot, but it's not really a plot. This plot just says, in the last few years, this machine has been running almost perfectly. I mean, very, very close. I mean, it's absolutely amazing, far better than we expected it to. And we've been taking huge, huge amounts of data. And we're running this machine now. It's coming to the end of its initial run, and then we're going to pause for 4 years, and I'll explain why. But this has been, exceptionally exceptional. Doesn't make much sense. We've made many discoveries. The Higgs boson was the big one. We've measured its properties. We've discovered 80 new particles. These are not fundamental particles. These are states made up of different hadrons. Measured properties of things we've never seen, humanity's never seen before. Huge number of measurements. I'm not going to go into the details here. But just to put it in the sense, these four experiments combined have produced about 4,000 publications. So scientifically, this machine has been incredibly, incredibly productive. So we know a lot, and we've measured a lot, but there are many, many deep mysteries, things we know that we don't know, and I've got 8 of them here. Why is the universe made of matter and hardly any antimatter? So in principle, Big Bang, you make matter, antimatter, it wanders around a bit, comes together, and you've got nothing left. That's not what happened. So we know that for every billion antimatter particles, at some point, there had to be a billion plus 1 matter particle. But we don't understand why. So that we don't understand that. We know that we've only seen 5% of the matter in the universe. There's dark matter and there's dark energy out there. So we don't know, and we don't know what it is. We don't know if the Higgs has anything to do with the dark matter. Does the Higgs interact with the dark matter? We don't know if the Higgs is a fundamental particle. Is it made up of some other stuff? Is it more complex? We don't know. We don't know why gravity is so much weaker than all the other forces. I said there were 3 generations of particles, the electron, a heavier electron, and an even heavier one. Why? We don't know. We know that that's probably true, but we don't know why. All of these particles we see have different masses. There's a pattern of masses, semi-pattern. It's not like the periodic table. But we don't know why they have different masses. We don't know why they have the pattern they do. And there's a very special property about the Higgs potential, the thing that makes the Higgs different from all the other particles. And that will determine the stability, ultimately determine the stability of the universe. The universe could just collapse into, well, not a very bad place. And that could happen in about 1 trillion years' time. Not something we worry about. These questions are really, really deep, and we don't have the answers. But we know we don't know the answers. So there are gaps in our knowledge, and we know what our gaps in the knowledge are. Half these questions have something to do with the Higgs boson. And that's really why the Higgs boson has been a big focus of our science. So just to, when we talk about why do all of these particles have different masses, now I said earlier, the Higgs is the thing that gives particles property that looks like the mass. So this is all about the Higgs boson. So big questions out there. So what next for CERN? What next for particle physics? So where is the next major discovery coming from? That's a question you should ask the panel afterwards, and they'll give you a definitive answer, perhaps. The answer is we actually don't know. I mean, we don't know where the next discovery is coming from. But we kind of know that it's actually okay not to know, because discoveries are, by their nature, things that you're not expecting. The important thing is we are looking in all of the right places. I gave you 8 examples of big questions we don't know the answer to. So we want to know the answer to at least one of those questions as soon as possible. So we have to look at the Higgs boson. We have to search for dark matter. We have to try and understand neutrinos better, because they could hold the key to CP violation. The pattern of flavor, which is really the differences between the different types of particles, and including their masses and CP violation, we're looking at there. We're looking at cosmology. We're looking out into space, trying to piece together large-scale structure in the universe with our particle model. So we're looking in all of the right places. And at some point, we're going to make this massive breakthrough, and the standard model we have today will no longer work. But we don't know when that's going to happen. The other thing we're doing, we're planning for the very, very long term. And this is why there are roughly 500, nearly 600 particle physicists in Helsinki today, this week, just over the road, talking about a project that we hope will happen at the end of will be running at the end of the 2040s. Very, very long time scales. This is called the Future Circular Collider, and I'll say a couple of words about that before closing. So firstly, I just want to say what next for CERN? What are we doing next? I've already said we're about to switch off the Large Hadron Collider, pause it for 4 years. And we call this a long shutdown. It's a very long one this time. This is for a major upgrade of the Large Hadron Collider. So picture this 27 kilometers circular ring, the collider. What we're doing is we're replacing the magnets, the most complex magnets, in about 1.2 kilometers of that ring, two sides of the big general purpose detectors. And we're replacing those magnets with a technology we just did not have when we built the Large Hadron Collider. This is just a picture of the test stand, also showing how international our collaboration is. We don't just collaborate within Europe, we have partners from outside Europe. But it's new technology, important new technology. It will give us roughly 10 times more brightness, so the machine won't be higher energy, but it will be brighter. We'll produce a lot more data. And that already tells you that we've only just started the LHC journey. We're about a tenth of the way through the whole of the history of the Large Hadron Collider and all the data we're going to get. The other thing we're doing, those giant detectors, these giant building-sized imaging detectors, we're upgrading those with new technology, better technology, the technology we just didn't have when we built the detectors. And the analogy I always like to make is it's upgrading your iPhone from an iPhone 2, no, maybe iPhone 2, iPhone 3, okay, my colleague says it's an iPhone 3 to an iPhone 17. That's the kind of giant leap in the technology we're installing in these detectors, so we get better photographs, because obviously phones are mostly cameras. But it's a big step forward in technology in the detectors as well. And all of our brilliant young scientists are developing new tools. A lot of use of AI, enhancing the way we analyze data. That will give us greater power. So this is an incredible, incredible scientific opportunity. A lot more data, better detectors, new techniques, and real discovery potential. Real discovery potential. And so it's very, very exciting. This is our mission for the next 4 years, is to construct this new phase of the high luminosity, the new phase, the high luminosity LHC. Beyond that, the reason we're in this beautiful city today is we're thinking about the project after the Large Hadron Collider. So that will finish in 2041. The case for doing this is partly built around the Higgs boson. We found this new type of matter, and it is a new type of matter. It's not just another particle, it's a new type of matter. We want to study it, understand what it is. So the case for a Higgs factory has been around for many, many years. Make lots of them, create lots of them, see what they do, study them, and, well, we'll see, use it as a window on the universe. This new collider, this picture here, I can't control it. There's the Large Hadron Collider ring, 27 kilometers. The future circular collider would be 91 kilometers. So it's a much, much bigger collider. The first stage, we collide not protons, but electrons and positrons, many reasons for that. And it has this really rich scientific program, Higgs physics, much, much more. And I think over the last few years, we've started to realize how broad the scientific program of the future circular collider is. We would like to start operations in the second half of the 2040s. And to do that, we have to take a decision on this machine and start investing in a few years' time. And that's really one of the focus points of this meeting today. Just a few weeks ago, the council, the governing body of CERN, updated our strategy and said, this is the right machine to build, scientifically the right machine to build. And they kindly asked me to go and find the money. And that's why I'm here today, and we'll be going around with the begging cap afterwards. No, that's not quite true. The total cost, though, is 15 billion Swiss francs. Now, that's either a very large amount of money or a modest amount of money, depending on your perspective. It's spread over 15 years. It will be shared amongst all of the states of Europe and beyond. So this will be ultimately be a global project. So it's incredibly exciting. Suitably, I'd say, ambitious. I mean, this is definitely an ambitious project. It's more than particle physics, though. It's a global leading scientific project at the heart of Europe. This is an area of science where Europe is way, way ahead of the rest of the world, way ahead of the US, way ahead of the East. So we have global leadership, and we have global leadership in a very, very high technology area, and that has a lot of value. It's not yet approved. We're hoping for a positive decision in 2028. That's our goal. And I think that's why there's so much excitement in this meeting we're having just over the road now, that 2028 is only 2 years away. We are soon going to know if this is going to happen and start not just talking about the design, but actually thinking about implementing it. I wanted to just say, I'll come to an end. I just want to say one thing, one slide on the benefits of CERN, wider benefits. If people have questions, I've got examples at the end, and maybe I'll show one example, actually. Firstly, I'm a physicist, particle physicist. We do this for the science. We want to understand how the universe works. And particle physics and astronomy have made incredible contributions. My personal view is that this is more than science. This is about understanding the universe that we, humanity, actually live in. So I think there's cultural value, not just scientific value, and I think that's incredibly important. Sometimes people talk about science diplomacy. So countries come together at CERN to work to a common aim, and have been doing so for 72 years, reliably, despite changing politics across Europe, changing differences, opinions, almost even within Europe, the world is, I'd say, a little bit more fragmented than it used to be, and outside Europe, obviously, even more so. So science is a domain, an area where nations can come together and do something really positive, a really positive goal, understand the universe, and come together and make a positive contribution. This was true 72 years ago, when CERN was first built, constructed, very, very early days, but it's true today. This is a place where the world comes together to collaborate. And there are direct economic benefits as well. We push the boundaries of technology constantly, and I'll give you one example, and then I will wrap up. We also train many, many young people in all sorts of technology areas, applications of artificial intelligence, but it's huge. Can't really do the list. And the last one, I personally believe our science is really inspiring. We are doing something quite remarkable, and I think that actually is really important to bring the next generation into subjects like science, technology, and mathematics. I'll give you one example about innovation and technology. Just one. It's my final example, my only example. This image, it's not, it looks like some cave painting, doesn't it? Or this is an image of various viruses being disrupted in situ. You can see these are spike viruses, coronaviruses. You can see the spike proteins. What does this have to do with particle physics? That image was taken using technology we developed for the Atlas detector. So if you used your iPhone sensors in these detectors, so we have a lot of silicon sensors in our detectors. If you used your iPhone in there, it would die. The silicon would die very, very rapidly. So we worked for many, many years developing silicon that could survive the very radiation-intense area of the machine. You ask yourself, is that going to ever have any relevance to society? Radiation-hard detectors, that's not very useful. But back in 2017, Richard Henderson and a colleague at EPFL in Switzerland won the 2017 Nobel Prize for Chemistry because they developed a new technique called cryo-electron microscopy. This allows you to freeze biological molecules like viruses and basically see them mid-movement and image very large-scale objects. This technique has revolutionized biology. So now if you talk about biology and understanding protein structure, your go-to technique is cryo-electron microscopy. It required very radiation-hard sensors. So the team working on Atlas, actually in the UK and in Switzerland, they collaborated with the people developing cryo-electron microscopy and enabled this technique. So this is one of the examples whereby pushing technology to do particle physics, you change the world in just like the World Wide Web, but in a different way. This has really revolutionized biology, though, all made possible by new technology. Final words, hopefully I've given you a bit of a sense of what we're trying to do at CERN, why I find it so exciting, and hopefully you do too. Simple, just let's understand how the universe works. Also, hopefully I've given you a sense of what you have to do to actually really look into the universe in this great detail, and the engineering that's required. And I didn't have time to go into some of the depths of why, the benefits beyond forefront research. But those benefits are there. We push technology. Pushing that technology gives us new capability. New capabilities could find their way into industry or into science and bring really large economic benefit. But you don't know what's going to happen when you're doing that technological development. The final point, we have a really exciting future ahead of us at CERN. It's all coming ahead in the next few years. We're building the high luminosity LHC, or we soon will be, and we are making plans for the next step, the Future Circular Collider, and much, much more is going on. So very, very exciting times. Kiitos.
Thank you very much, Mark. Super interesting.
Cheers.
Thank you very much. Any questions from the audience to Mark Thomson? It's always, there's one. Yes, brave man, first one to ask a question. There's a microphone.
From what do you take those protons which you put together in this field?
So what we do is we take, you can imagine just taking one proton and we accelerate that proton to the speed of, very, very close to the speed of light. So it's going around very, very fast. Where it comes from. So the whole of the LHC starts in this little bottle. It's like a beer can of hydrogen. It's tiny. It's about that size. And we're never going to use it up because although our beams are very powerful and there's a lot of energy in them, we don't use very many protons. So we basically take hydrogen atoms, we actually add an electron to them to make them charged rather than neutral, and then we accelerate them, and then we take the electrons off, and then we put them into another ring, and then another ring, using very, very powerful magnets and very, very strong electric fields. But ultimately, it comes from a small bottle of liquid hydrogen. I really should have a picture of it, because it's very unimpressive.
Good question. Thank you, sir. Any other questions from the audience? You have to help me out here. I don't have any questions prepared, so please help me out here. I will come up with one, for sure, if there's no one else in the audience. What about you? You're already holding the microphone. Do you have a question? No questions? Oh, there's one.
Oh, there is.
Gentleman over there.
Yes, so thanks for the nice talk. You said that it would begin operating in the 2040s. When would the construction begin if everything goes as planned?
So if we had a decision in 28, which is what we're aiming for, it then takes about 4 or 5 years to finish the design, construction, and put in place the contracts. Because part of the project is actually building a 91-kilometer tunnel, 200 meters underground. So there's actually a lot of preparation you have to do before you say, let's go, and preparation for the project. So it's like 4 or 5 years before you really start the very, very large investment. But before you start, you've got to know you've got the money. You don't want to start and then stop halfway through. That has happened before in the United States. That's an interesting, different story. We don't want to do that.
Thank you.
There's a non-physicist there.
That's great. I love that you're asking a question.
A non-physicist who might be a physicist in disguise.
Well, at least I have a non-physics question, because it's a finance question. I'm sorry. So you said that the CERN management or probably CERN board or something kind of gave you this modest task of trying to find some of these missing budget from this fairly expensive future plan. So what is your strategy of where can you find this additional funding?
So there's a number there, 15 billion Swiss francs, not euros, 17 billion, 16.5 billion euros. So it's quite a large number. More than half of that can be found from CERN's budget. So CERN, we have a budget from our member states. It's constant, very stable. So rather than, once we've stopped operating or stopped constructing the high luminosity LHC, we can start directing some of our budget towards the Future Circular Collider. That's a little bit more than half of it. Then we have to find other sources. A major potential opportunity is from the European Union directly. in the draft, and the word is draft, multi-annual financial framework that is being negotiated and discussed in Brussels right now. There's a possibility of the European Union directly funding 20% of the project. That's about 3 billion Swiss francs. So that actually, what we've got from CERN budget, 3 billion from European Union, and that's really all focused around European scientific and technological, I won't use the word supremacy, but it's really that, keeping Europe at the forefront of technology. We also have pledges of almost $1 billion or €1 billion from donors who just see that this is a project that's good for humanity. So you can start to see ways of it adding up, and then we will be speaking to countries outside Europe. At the moment, the United States is a very major contributor to the high luminosity LHC. So you need to build up this pile of, puzzle of money to get to that 15. There are ways we can do it. And I'm reasonably optimistic we'll get there. It's not going to be easy, and that's why I'm also clear it's definitely not going to be easy. But it's a big ask, but it's definitely not an impossible ask.
Following up on that, actually, how many? What is the ratio of people who are sitting on the money, whether it's private money or taxpayer money, that you want to fundraise?
Oh, that's a really good question. That's a good question, actually. That's a really interesting question. We are a publicly funded organisation, paid by the taxpayers across Europe. I don't think we ever want to get into a position where we're reliant on donations for the future of CERN. Sure. The reason CERN has done so well and has been so stable and has lasted 72 years, which is a long time, is we've had this constant commitment from our member states. So we can't rely too much on outside private funding through donations or otherwise. What's the right number? It's definitely not 20-30%.
Right.
So that's something we just need to bear in mind. We could probably go up somewhat beyond where we are today, but
when you fundraise and speak with them, what arguments resonate the most? Is it this research has some instrumental value, we can create other products, or is it the pure the value in and of itself of discovering new things about our universe?
So my predecessor was the one that managed to get most of the existing contributions, but I do obviously speak to some of the key donors. They see this as being good for humanity.
Yeah.
I mean, really, it's as simple as that. And they don't want anything in return, which is pretty amazing.
That is amazing. Wow. Any other questions from the audience? Yes? Oh, there's one. Great. You're next, and then you, sir.
So hi. So if I understood it correctly, so like the accelerators generate lots of energy. So can you reuse it to somewhere else?
No, because we're not creating energy. What we're doing is we are taking our particles and we're putting a lot of energy into those particles, but you have to use energy to do that. So we've now got particles with a lot of energy, but we've put the energy into them. And then when they smash together, it's effectively using Einstein's equation E = mc squared. So we've got a lot of energy, so we can make mass, new particles. But we're not creating energy. It's quite the opposite, actually. Sadly.
Interesting. I don't know why I'm nodding. I have no idea what this is all about. But you, sir, you had a question.
Thank you. I will pretend I am a young Finnish, and I would like to ask you what you would tell me to motivate me to join CERN as a young professional.
I'm biased. It is the most wonderful, incredible organization, scientific organization in the world, doing the most incredible things, exploring the universe in ways that have never been done before. It's an amazing place. You just need to, well, you've been there. You just need to sit in the cafeteria and talk to the other 1,000 or so scientists from 100 countries, all talking about physics. Soon they'll all be talking about the World Cup, but usually they're all talking about, it's a very vibrant place. what we're doing is important, and it's great to work on. It's really, really fun to work on.
This is a question. Sorry, you had a follow-up question.
I mean, just to say, I am a CERN staff.
You are CERN.
And I can just confirm. Absolutely.
Very good.
If you both want to answer this, it's fine with me, actually. I'm going to ask the panel this question. A lot of young, bright minds these days are going into quantum computing, AI, even finance. A lot of people are going to, probably because they're motivated by the possible riches that they might acquire. How much does the pure joy and awe of discovery still motivate the young, brightest minds these days, or is brain drain a real problem for CERN?
I think it very much, you can ask the panel that, but I think it very much depends on your personal motivation, what matters to you as a person.
Sure.
And many of us see this mission as something that we really value and we want to be part of.
Sure. That's good. Any other questions? Yes, now they're coming. There you go. Oh, just so the stream can hear it.
Oh, yeah.
Hi, it's not such
Thank
an
you.
important question, but thank you. I was wondering about science communication. Like, especially actually right now in the age of AI and education is very much changing. What is CERN doing in order to further educate the public about these findings?
So we do have a big science outreach campaign. We know our science is valuable, it's very exciting, it does inspire people. In terms of education, it's kind of difficult for CERN as an organization that's sitting on the Swiss-French border to really make a massive difference educating directly. But what we do, and actually in terms of Finland as well, Finland benefits from this, we actually have a program where we educate the educators. We bring teachers, very large numbers of teachers, to CERN. We actually bring large numbers of students to CERN as well, but of course, there's only a certain capacity. We bring teachers to CERN from different countries and actually talk to them about the science, what CERN is doing, how to communicate that science within their own classes. So by teaching one teacher or inspiring one teacher, you inspire classes of pupils, or you have the potential to do that. So that's really one of the mechanisms we use, and it's very, very effective. And it works really well. And it's because you're multiplying. We also have an education center, a science education center, that attracts about 400 to maybe 500,000 people per year into. My colleagues can give me a better number. I'll call it 400,000. 400,000 people come to this. It's not a science museum. It's really a kind of science education center. It's the #1 tourist attraction in Geneva. So we hit almost 500,000 people a year. That's pretty impressive. So we do what we can. It is important. It is important to us. I mean, again, just as a publicly funded organisation, we try and support education particularly in all of our member states, including Finland. I can't hear you. Oh, and there are online courses being, So there's a lot of other stuff, but yeah. We do what we can.
Great.
And we are always looking to do more, actually.
If there are no other questions, give a big round of applause to the Director General of CERN.
Thank you.
Thomson, thank you very much, Mark.
Thank you.
Thank you. Next up, it's time for the panel discussion on the future frontiers of, I forget which kind of physics we're talking about. Something. Fundamental physics, I think. Let me see. Can I invite all of the panelists up on stage right at this moment, and then we'll introduce you while you are already up here. Meanwhile, I will actually check and see what the actual name of this panel discussion is, because I am hosting it, so I should definitely know. Future Frontiers of Particle Physics. And we have 6 distinguished panelists here with us. Give them a big round of applause. Thank you very much. And I must say, we always stress about this before we hold these events. As a moderator, I think about this a lot, and I share my concerns with all the organizers every time. But we did get a very nice turnout this evening. It's very nice to see the physics it can draw a crowd like this. So thank you all for coming. But I would like to introduce our panelists tonight, and I will give you, the audience, your name and your title and your university, and it would be nice to hear a brief introduction of what kind of physics you work with these days. So let's start with Rebecca Gonzalez Suarez, a senior lecturer and associate professor from Uppsala University. Welcome, Rebecca. What kind of physics do you do? Yeah, you should get a microphone. Absolutely. Do you have a microphone? Yes. Great.
Is that one working? Awesome. Well, thank you so much. Well, I mean, I do work in FCC. We're looking at new physics. I also work in Atlas, also looking at new physics. I started my career looking for the Higgs boson. It was fun. We found it. So I'm all up for it.
Good job, Rebecca. Then we have Anu Kankainen, Academy Professor from the University of Jyväskylä. Welcome, Anu. What kind of physics do you do?
Well, I'm a nuclear physicist, and I study exotic radioactive nuclei that are produced by accelerators, for example, with the one we have at the University of Jyväskylä. But I have also been involved in, like, for example, my first PhD experiments were done at CERN with the so-called Isolde facility. And I'm also involved in this forthcoming FAIR facility, which will be commissioned in Germany in forthcoming years.
Amazing. Thank you very much. Welcome, Anu. Then we have Panja Lukka, a professor at Lappeenranta University of Technology, and also HIP, right?
Yes.
That's right. What do you do?
So I'm actually building the detectors, basically. I'm one of the persons who kind of designs the detectors, tests them for the reliability. So, because somebody has to build them, in fact. And it's a lot of physics involved in that also. Like Mark mentioned, actually, the radiation hardness, that is one of my research topics, actually, that we try to find detectors that last better the radiation that we want to measure, actually, in the experiments.
Amazing. Thank you. Very welcome. And then we have a real respected veteran of the game here. We have Professor Michelangelo Mangano, a serial theoretical physicist from CERN. Welcome, sir.
Thank you. Yes.
What do you do, Michelangelo?
So what do I do is to try to describe what happens in these collisions that were described earlier by Professor Thomson. We start on the basis of those particles that he illustrated and their interactions, and we model what happens at the LHC. We tune our understanding of nature, and if we see any deviations from what we expect, that is a signal of possible new physics or new phenomena. That's the way the Higgs boson was described.
Great. Thank you very much, and welcome, Michelangelo. Then we have Mikko Voutilainen, professor at the University of Helsinki, also AHP. What do you do, sir?
Yeah, so I'm working on the compact muon solenoid experiment. As mentioned, that is not very small, it's actually big. And I'm working on calibrating the data in order to just measure how heavy is the heaviest particle top quark, how strong is the strongest force, and then if the whole vacuum will collapse, like was mentioned. This was the last question. Is it even stable?
Amazing. Welcome. And then last but definitely not least, we have professor from the University of Helsinki and HIP as well, and also a former guest of my own podcast, FutuCast. Go listen to that episode, a small plug. Don't mind me. What do you do, sir?
Hi. I'm a particle theorist by education, but I have to admit that I understand remarkably little about particle accelerators, even though I was a fellow at CERN for 2 years in 2008 and 2009. But rather, I study elementary particle matter in a very different context, in the cores of very massive neutron stars, where we may have a completely new state of matter composed of quarks and gluons called quark matter.
Great. Welcome to you. And actually, I want to start the panel discussion from that side, Alexei. First question. By the way, I'm going to direct these questions to one or two of you at a time. If you want to say something, if this is a question you feel is very appropriate to you, you have something to say, you can raise your hand or just feel free to interject so that we don't miss your answer if you want to. Okay. Is particle physics living through a frustrating plateau right now or in a period of underrated success? What do you think?
Very good question, and kind of non-trivial one to answer. So in one sense, certainly it's been a very successful run so far, and the fact that the Higgs particle was discovered at CERN was really a triumph of, dare I say, theoretical particle physics, in the sense that something that was predicted already in the 60s because of largely sort of mathematical beauty and symmetry was seen to be true and realized in nature in exactly the way that it was originally predicted. At the same time, of course, everybody was hoping that something new, something unexpected would have come out from the LHC, and maybe that will still happen one day. And I wouldn't call this a plateau or any kind of a crisis, certainly, but at the same time, we are knowing very well that there has to be physics beyond the standard model. It would be fantastic to find more direct signals from somewhere and really be able to tell what's happening. But this is not really my personal expertise. So it would be interesting to hear other opinions as well.
Is there anyone whose personal expertise this is who has something to say about that? Michelangelo, go ahead.
I'm one of those who fights very strongly against this perception of the status of our field. Mostly comes from our own attitude, rather perverse, towards what we do. Indeed, as we just heard, we are looking for possible phenomena beyond the standard model to find answers to the big open questions that we saw before. And that means looking, say, for a new particle. And when that particle is not found after a long search, we always end up saying, we failed to find an inconsistency in the standard model. In other words, we transform a positive statement like, we confirm that the standard model, our understanding of nature is very strong, into we failed to find inconsistencies. So when we say this to the public, they only hear two words: we failed and inconsistency. So clearly that gives a very perverse impression of, and that also percolates through our community. The reality is that the achievements that we've obtained in the past few years in getting to this point are absolutely extraordinary. We have an understanding of nature which is unparalleled in any other area of science. And in fact, it's precisely because of this that we can afford asking those questions. Before, you have to find the what and the hows. And once you understand how things work, then you can start understanding why, which is the deepest question, the most challenging one, as we also heard before. So I find it very exciting, and I do see that right now this excitement actually resonates with the young generations. AI is helping a bit because it's giving them a sort of entertainment, to go together with the science itself. There is also this little challenge, these toys to play with to make it even more exciting. But it's, I see growing enthusiasm, and we just saw it. 4,000 papers have come out of these experiments. And those are very deep new results and information on how the universe works, things that we should be talking about, not just about dark matter search, etc.
Just so that I understand, when you said that the statement after the discovery was made was we didn't. Can you say, what was it again? We failed to prove any inconsistencies.
We failed to find an inconsistency with the standard model,
right?
Which means everything works as it should.
Right, which is, first of all, I mean, I guess you have the burden to falsify the hypothesis as a researcher, but also, like, does that then mean that you don't have anything to begin to explore, to explain many other unexplained things in the standard model? Is that what that means?
It just means that things are more challenging. It means that nature is more subtle than we can imagine. We do have models, ideas on what dark matter could be, but dark matter could be a huge variety of different things, and we need to do gazillion experiments of all different sorts to probe it. And at the end, only one of these experiments will be right, and when that happens, it will really be a revolutionary discovery. In the meantime, you have to work. But while you do it, you also discover many other things. We've been discovering 80 new particles at the LHC, in addition to LHC. Their origin is, the deep origin is understood, but the details of how they works, they are not. So there are many open issues, even at the sort of less deep level than the big questions about dark matter and dark energy.
Interesting. Rebecca, you said you were involved with the discovery of the Higgs boson. You were there. I'm sure other people helped as well, but
it was only me.
It was just you.
Yeah, it was a solo.
Well, good job. Can you bring us back to that moment when it was being built, or before you were able to participate in the actual experiments? How did that feel? What were the expectations like at that moment, and did the expectations were they fulfilled?
I mean, it was a really great time. I arrived to CERN as a PhD student. It was my second year, so it was 2008. I met Alexei. It was pretty cool. We had good times. For me as a student, I didn't know that this was not the normal. So I really loved the energy that was around. I mean, we were building this. Many things were not going according to plan, but then we pulled through, right? We had incidents, we overcame it. It was really fun. Everybody was really excited, and it's impossible not to arrive there at a time and then, yes, want to stay there forever. And this is exactly what I wanted to do. It was like, okay, this is the thing. So it was a really cool time. As an experimentalist working in the search of the Higgs boson, I was sure we were not gonna find it. I was 100% sure we were not. And a lot of people were telling me that we would not find it. Mm-hmm. They were like, oh, there's going to be other particles, there's going to be technicolor, there's going to be whatever. So it was really interesting, the fact that we actually did find it. So it was pretty amazing. But I think I have only learned to enjoy it after the fact. So now I enjoy it better. It's like, you need to get a little bit of distance. But I think it was a real privilege to be there at the time, and I think it was really amazing.
Anu, what was that like? Do you remember that moment when it was discovered? How big was it for you and for the field itself?
Well, I remember, of course, from the news that, okay, it was announced and it was amazing. And for me, it was kind of expected, so it was not that a huge surprise, although it was wonderful news, but something that like, hey, science works.
Very interesting. Actually, I do want to ask the remaining panelists who I haven't talked to yet about this, because this seemed like it was a big moment. I mean, obviously it was, even spilled out to the real, quote-unquote, real world of not physicists. So, how was it like for you?
I'm also a physicist, even if I'm doing detectors. So, in that sense, but yeah, I mean, I have been working actually in the CMS detector past 26 years. So, of course, I talk now from the CMS perspective. I mean, it was a great discovery. And we were, of course, super excited about it. And then I think it was a good decision from CERN to actually that CMS and Atlas publish the results together so that there is no competition in a sense that who can do it first. But it was a great moment.
Mikko, were you as satisfied with the results, or did it leave something in the back of your mind?
It was a big impression. I was a postdoc just having started there. I knew that we had the Higgs boson coming up. A few weeks before the world knew about it, we had the internal seminar where we were just opening the box a day before. So I arranged to be able to be at CERN on that date. Went to the room, super packed, super hot. All the internet connections to the outside world were breaking up, even within the collaboration. And then it was really awesome. We saw a few channels coming up. The photon channel, 4 sigma. Then we had the W channels coming up. ZZ channel was 3 sigma. So just doing the calculation in my head, okay, now we are at 5 sigma, so this is going to be it. So that was really nice. Going back to the hostel in the evening, I wrote about this experience so that I would forget it, put it there in a box so that I opened it up for a few years. And one of our colleagues from New Zealand, from the theory side, had actually this blog called Trenches of Discovery. So we published those memories there a few years back. So it was a really awesome moment, being there and knowing something that the rest of the world would only know in 2 weeks or so.
Very interesting, yeah. Michelangelo, compared to, or contrasted to your expectations of the LHC before it was operational, and to whatever extent those expectations were fulfilled, How do you compare that to your expectations right now of the high luminosity LHC and possibly the FCC in the future, and to whatever extent you feel like your expectations will be met regarding those?
Like everyone else, I was counting on the Higgs discovery, and I was hoping that there would be also some other signal of new physics, dark matter, etc. I mean, I was not frustrated by the lack of new physics, as I just said before, because I saw many other things happening from the LHC. And all of those other things far exceeded any expectation I could have had. One of the concerns before the beginning of the LHC was whether we could manage the overall complexity. This was a problem that was affecting everyone. The accelerator is very complex. The experiments are very complex. The theoretical calculations are very complex. And we were all called to meet the highest standards, to meet the challenge. And the point is that on all of these three fronts, the goals were far exceeded. And it's really incredible, the overall coherence in the response that the whole scientific community obtained. And this allowed us to get results which are, 10, I mean, maybe more than 10, because 10 we were already running, but 15, 20 years ago, when we were preparing the physics scenarios, nobody would have expected anything like what we have today. And this doesn't set a theorem. It doesn't say that the next enterprise will be equally exceedingly successful, but it certainly tells us that our ambitions can be very high. We can meet them. The community is so strong that indeed it can achieve, and therefore I have full confidence, let's say, that the next step, which will be high luminosity, and then later FCC will deliver and will surprise us as much as the LHC has.
Are there any questions that are as defined beforehand as the question of the Higgs boson was before the LHC was operational that exist right now that might be answered, that you could make a well-educated guess that this might be answered by the high luminosity LHC or the FCC?
Well, the only thing that can be answered are what I call the guaranteed deliverables. You know that something exists, you don't know it very well, and you want to improve your understanding of that something. And then that allows you to set goals. If everything works as it should, you're going to get those measurements with that accuracy and learn something. When it comes to discovering new particles, the Higgs was the very last one on which you could bet your career and your salary. There was a theorem that guaranteed the existence of the Higgs boson, and that it would be discovered by a machine like the LHC, if the LHC functioned as it was supposed to. Right now, we don't have that. So all of the big questions that we've seen in the presentation, what's the origin of the Higgs itself, what's the origin of dark matter, what's the origin of the three families, etc., there are many theories that could answer that. But we still don't know which one is right, and therefore we don't know which one to bet on. And therefore we will have to see. But what a machine like this guarantees is an improved measurement of how nature works at a much deeper level than we ever knew. And throughout history, the centuries, there are infinite examples of precise and detailed measurements that at the time looked like, pointlessly adding one more decimal to, and that eventually turned out to be absolutely critical for when the new physics had to be discovered, right? So we are leaving behind for the future history really very valuable information to interpret whatever new physics will be discovered.
Yeah. Are there any panelists? I realize this is a brave question to answer to, since we have the Director General of CERN here, as well as senior researcher, but is anyone skeptical about this? Do you have any skeptical comments, like any questions about this? I see you're biting your lip, Alexei.
Well, certainly not skeptical about whether FCC should be built, but one should somehow first define what we are skeptical about. But one very non-trivial question that I think should be asked is probably that when the time scales of a new project are tens of years, and we are right now undergoing this sort of AI boom where technology is developing in ways that are extremely unpredictable, then I don't know, maybe Panja is the right person to ask this, or somebody who is really responsible with kind of designing the kinds of detectors that we would be then using in 20 years from now. So do you see this as a real challenge that we don't, it's extremely challenging to predict what kind of technology we will have at the point when the FCC detectors would actually be built, or when the whole machine would be started?
And remind us again what year that is.
Sorry?
Remind us again what year that is. How far in the future?
I guess we're now talking about the 40s, mid-40s or something like that.
48 or something, I remember seeing.
Well, it was, I think it was a little bit earlier, but in any case, I mean, we finished basically with the high luminosity LHC more or less 2041, and then should install, of course, basically the next generation accelerator if we build it. So, of course, it's true. The technology is one of the actually very important parts, and it's technology that doesn't already exist. We need to get better. We need to get better detectors. We need to get even better magnet technology. So it's kind of a challenge. Of course, like was mentioned before, it is actually very important for the society also, because this is a driver of technology, because we really need to build something that doesn't exist on the shelf of a shop. So that pushes us to find solutions that are better than before. And that, especially in the, if I talk about my own subject, like detector technology especially, it means that we really need to get much better than we are currently. We need to have higher resolution image. We need to have more radiation hardness, because the more we collide particles together, the more there is radiation. And the same radiation we want to measure actually breaks the material. So they need to stand more and more, because we cannot change them every week or every month or even every year, because it's just very difficult to access the detector, and also basically we cannot afford it to do it too often. So we need to find better technology that can actually stand in these conditions, because they are quite harsh environmental conditions. But then if we think about it, I think basically, technically we can build detectors that can see the particles. Okay, again, of course, the tracking detectors, which are the innermost detectors, they measure basically where the particle went through. So I believe we can do that, even with the kind of currently existing technology. Our main challenge is actually to basically have it radiation hard enough that we can operate long enough that we can find these rare particles. So actually, there are many these kind of challenges. But if physicists who develop the theory can actually tell us what we should measure, what we should find, I think we can build the technology.
Yes, go ahead, Michelangelo. Also, Rebecca, I see you itching to answer, or are you? Okay, it's fine. You're just.
Yeah, I have an opinion about this.
Okay, let's see. We might come back to you. Michelangelo,
it was
go
just
ahead.
a remark that this is one of the things that differentiate between this community and other, either scientific community or technology, etc. They build and they plan on the basis of what is available very often. You know, going to the moon, they made a design in 62, 63, and the electronics, whatever they had in 69 was what was available then. We design our future detectors, accelerators, on the basis of our assumption of what will be available at the time in which they have to operate. The LHC detectors were designed, you know, in the mid-1990s and later on, and what is actually went into the detector was not available at the time. The computing, all of the ability to measure and compute and record the data were tuned by extrapolating the curve of progress in processors, etc. So this means that even though we're planning now, but in 20 years from now, we will really be at the edge. AI is a different story, I mean, because that changes a bit the rules of the game, right? And we don't know how it will impact, but technology-wise, this is the experience. It's really looking forward.
Yeah. Yes. Are there any other avenues of discovery in the frontiers of fundamental physics, particle physics, outside of these large particle collider experiments, Anu, that you are fascinated by?
Yes, indeed. Like, for example, in my research field, there are several smaller scale projects that, for example, one can study beta decays of specific nuclei and try to probe if there is physics beyond the standard model or what kind of physics there would be. And yeah, there are quite many exciting experiments ongoing at several places. And also, as was mentioned earlier, it's not only like nuclear physics or particle physics, but also like astrophysics and astronomy, like all these gravitational waves, multi-messenger observations, and all that stuff also brings new information and new discoveries for fundamental physics.
Don't worry, Mikko, I haven't forgotten about you, but Alex is holding his hand.
Yeah,
Go ahead and comment.
Just a very quick comment that one particular sort of experiment or mission that is worth highlighting here, I think, is the LISA satellite that will be flying hopefully in the mid-2030s, which hopefully will be able to see a gravitational wave, or if there was a first-order phase transition in the very early universe, which is a rather generic prediction of many BSM models and is a prerequisite for something called electroweak baryogenesis to work, which is one of the leading explanations for why there is more matter than antimatter, then this LISA satellite should actually be able to see traces, gravitational wave traces of this phase transition, and this, I think, is just one, but a very prominent example of these kind of complementary experiments that might be able to directly probe BSM physics that are not happening in colliders.
Very good. Mikko, I'd like to ask you the same question, actually. Let's do a round of this. What do you think are the most fascinating, unanswered questions in physics right now that you are most sort of stimulated by?
I would maybe put dark matter, even though I'm not working directly on that. It's a big question. We don't know if it's very massive black holes, if it's very light axions, if it's supersymmetric particles that we could actually see at the LHC, right-handed neutrinos. So just knowing what it is would help a lot, because now we have to look everywhere, underground, deep space, accelerated experiments. So this is a big open question, because it would really focus the field on the next avenue.
To a layman like me who doesn't really understand, can you describe our grasp of that question at the moment, and to whatever extent that grasp could be somehow firmer in the future? Is there any way to estimate something like that?
Right. So we do see that it's out there in space. We see that the galaxies are rotating. 90% has to be there so that they stay together. We see light bending around the galaxy clusters. So there's lots of evidence. We see it in primarily the early universe light. It's imprinted there. So we have very solid evidence that dark matter is there. So it's a really big mystery of why is it missing and what it's made of. And this is a long-standing question that was formulated over 100 years ago, that we first saw by the galaxy rotation curves.
Rebecca, what about you?
All right. I mean, I'm an experimentalist. I don't have a favorite thing, because I think that this will bias the way that I work. But I think at this point, with all the knowledge that we have gathered throughout the years, we know two things about new physics, right? So there is going to be something that is going to be very heavy, for which we need stuff that is very high energy, something that we cannot really target exactly which mass yet, or something that has some non-trivial structure that then might look a little bit different than the things that we are used to do. So this is why, coming back to tie it up to the project that we were discussing today, FCC, I think is interesting, because it allows us to actually target both. It is indeed very complementary, so like this possible first-order transition, we can also study it indirectly in FCCE, and then there are other things that can be taken later. So I think it's a very good example, actually, that you brought up. Then there is, of course, the kind of physics that you do is also complementary to what we can do in this area. There are many things that we can learn from each other, but there are certain things that you can only do here, right? I mean, only in a collider you can produce a Higgs boson, only in a collider you can produce a top quark. I think we need all the different approaches in order to get the full picture of the universe. You cannot only get it by looking at FCC alone. You cannot only get it by looking at LHC alone. You need all the other complementary areas. So, but okay, this said, I was lying a little bit. My favorite BSM case is like why the neutrinos have masses, but this is very complicated. I hope we can find a solution to that one, but okay.
Good. Anu, same question.
Yeah, for me it's still a very interesting question, this why is there more matter than antimatter? So I think that is like really most annoying because we know that, yeah, something is missing. We need to explain it, and there are quite many experiments trying to pursue that. And I agree with Rebecca that indeed, like there are lots of like synergies between different fields. And yes.
What about you, Panja?
Well, I think kind of, I mean, most of the people have described pretty well everything already. But in a sense, for a physicist, it's actually, in a sense, extremely boring if we know already what is there. So actually, for us, it's exactly this that we don't know. It's the interesting part, and we want to find out what we don't know. Because if everything follows the models extremely well and exactly, then there is nothing new to look for, but we have not that situation. Actually, they are not exact. I mean, they are quite well following, for example, the standard model, but there are still some kind of questions that is it really correct or not? And like was mentioned before, I mean, there are several theories, and now we should find out which are the correct ones. But yeah, beyond standard model physics and also this question of antimatter, those are extremely important and interesting, and also gravitational waves. There is a lot to do, although the collider experiments are not exactly the ones to do them and study them. But on the other hand, similar technology that was developed for example, for the colliders can be used also into looking into gravitational waves. So it's a big collaboration of physicists, and also something that is built for colliders can be used actually elsewhere, also in the physics and also even in the space research, actually.
Great. And then finally, same question to you, Michelangelo.
It's hard.
Yeah, there are not many left to mention anymore. All of them have been said already.
The dark matter, you know, without dark matter, galaxies wouldn't exist. They would not have formed. There is evidence that at the beginning of the universe, there was a need for dark matter to bring mass together and form galaxies. And without galaxies, we wouldn't be here because we have to go through the process of stars dying, creating heavy elements, regenerating, and finally get a planet with iron, silicon, etc., like what we need. So dark matter is really tied to life in the universe, in a sense. And where it comes from and why it's there is a big question. However, as I said before, it can be many, many things. Still, we haven't pinned down its origin to the point that we can build a dedicated experiment to guarantee its discovery. So it's really betting a lot. The other big question is, what is the origin of a Higgs boson, which is likewise, you know, related to really life in the universe. But for that, at least we know that, as also Rebecca said before, colliders are the way to probe the Higgs. And at least therefore we have an open window onto a possible direction in which answers to this question can come. So because of this, I find the question of what's the origin of the Higgs boson more exciting to me to be answered.
Yeah. This is the question that I asked Mark Thomson and that I wanted to ask you about young talent, about young physicists. I don't know if this is true, but I have an idea. There's a sense that many young people in STEM are going into the private sector, AI, quantum mechanics, finance, because of whatever motivation. Very understandable, I guess. But it seems like whenever I talk to physicists, like you just said very well, that you are sort of motivated in and of itself by the joy of discovering new things about our universe. That is a very sort of fundamental drive that I'm guessing all of you have. Does that drive still exist in young people, and is that drive enough to motivate young people going into fundamental physics in ways, the same ways as before, or are you actually seeing a material brain drain that is affecting your field right now? What sense do you have of this? I don't know who I would. You want to answer this? Okay, Rebecca.
Rebecca, you are the young one now. So.
yeah, represent them.
I mean, don't get fooled, huh? I'm 44. But, so I have an opinion about this. Because, I mean, I have heard this from many colleagues, but from the young people that I interact with when I teach in, the project students, master students, PhD students, it is the opposite. And I mean, one very clear example is that you put out a PhD position, you get hundreds of applicants. There is interest in the community. But what you said, that people want to do AI, want to do quantum computing, want to do stuff, want to go to finance, that is absolutely not incompatible with working in particle physics. I mean, those of us that stay in academia and doing experiments or doing theory forever, we are the rare cases, right? So when we're talking about something like CERN, is a massive place for education. Most people are at CERN just for a short time, for a couple years, for a couple months, for maybe 10 years, and then they go away. And many of these people are working in AI, they are working in quantum computing, and they are working also in different kind of like economy places. I don't know anything, I'm a physicist only. So I think it's really like, there is no need to separate those, and you can be motivated not necessarily by, okay, I think one of the things that we all share is that we like to solve problems. So we want to have a problem that is difficult enough, that is challenging, but also not impossible. And I think this is literally the thing. But also even people that are not super like solution-oriented, they can still have a space working in particle physics. I mean, we are a very large community, and I think very diverse profiles can apply. But honestly, young people really want to do this. So, I mean, if your young people don't, send them to me and give me funding. I think it will be great. We can solve this problem.
That's awesome. Yeah.
Was,
very happy to hear that. Someone else raised their hands. Yeah, Panya, you wanted to say something.
This one.
Thanks. So actually, I think it's not really the problem that people wouldn't want to do physics. They are very intrigued about physics. It's maybe the inherent academic way how we operate that only around 10% will stay in the academia. The rest typically find work elsewhere because there is limited number of professor positions, there is even limited number of senior permanent positions. Young come in, they are very excited, but then when they start having family, etc., they want more permanence. And that academia often cannot really offer. I mean, on rare cases, but often you need to do several postdocs, go abroad here and there, and it's not very compatible with, family, especially if you think about how being with the small kids or kids in the school, you cannot move from country to country very easily. So then some people actually drop because of that, even if they would love to do physics otherwise, but for these kind of reasons, they just consider the other fields more compatible with their current situation. They may even sometimes return back. I mean, there are cases who return back to the academia after being for a while in the companies, and then, so there is kind of exchange between the two. But on the other hand, it's not necessarily that it would be so different, the work. For example, if you think about data scientists who analyze the data, I have a very good friend who actually went to the Swiss bank to do kind of risk analysis. And he was telling me that actually, funnily enough, it was very similar algorithms that he needed to develop for basically for the stock market than he did for trigger in physics. So in certain aspects, it's not that far, although, of course, the topic is a bit different. I mean, we are working on the fundamental science and big questions, whereas in the bank, okay, you do it for profit. But still, it's not necessarily intellectually at all worse job to do it. But in any case, we have really bright minds who are educated at CERN and in the universities, and they are actually very wanted workforce in many, for example, AI companies, etc., because they really understand very well what they are doing. They are fast to learn. So these are skills that are actually very wanted outside of academia too.
Yeah.
So.
Michelangelo, Europe, as we heard before, leads the world in this field of study. Why does that matter? Why should that matter to Europeans, other than being very cool for Europe?
To me, it doesn't matter. I hate the word leadership. It's good, you know, when we talk to politicians, but in our community, I never heard that word being used.
Yeah.
And it can be very dangerous, in fact, to really express our excellence, which is an absolute concept in terms of leadership. As we saw again before, the LAC was built out of contributions that came not just from Europe, but from other countries. Without the US, without Japan, Russia, Canada, and others, we would not have had the resources to build the LAC. If you tell them that we build the next machine to ensure the leadership of Europe, they will feel like, why should I be doing this for you? Okay? So, and we don't do it for that. We do it because it's the right thing to do towards humanity, towards our understanding of nature. And somebody has to do it. We're all open. Many of us built their careers, spent years working in experiments in the US, in Japan, in Russia, in Germany. And this is how our community works. For the politicians, of course, now it's a critical time. The word leadership all of a sudden becomes important. And I think it's just a simple word to explain to the politicians that indeed something, I mean, the physics we do and the laboratories we build are a way for them to improve the welfare of the nations that they are responsible for and protect themselves against the possibility that maybe others develop the same technology but with different intents. So you want to guarantee yourself access to the best ideas and technologies. But literally for us, at least not for me, but I assume for all my colleagues, leadership is not the way to qualify what we do.
You were raising your hand, Alexei.
Yeah, I just wanted to add one thing that's also related to what Rebecca was saying just a moment ago, that there's some inherent value in trying to ask or trying to answer the hardest questions out there. That is one of the things that attracts the brightest young minds, and I think that CERN has a role to play in Europe in kind of ensuring that some fraction of our brightest minds actually stay in Europe and rather than going to work for Google or something like that in the US. So this is one thing where we are really at the top of the world, and it would be a huge shame to lose it.
That is true. Anu.
Yeah, I agree that the science is global and talking about leadership is maybe not very fruitful, but I find I agree with Alexei that CERN is very important for Europe. Like we don't have Silicon Valley, but we have CERN, and together with these very large, challenging projects, it creates innovations, and it's very important for European economy, I think, as well as for science globally. But there are several aspects that we need to consider.
We are slowly approaching the end of this panel discussion. I do want to reserve some time for audience questions, which I assume there will be some. I hope so, at least. So I will ask one more question, and it would be nice to get an answer from everyone. Let's see if we have time. So brief answers, if possible. First of all, thank you very much for doing this. Not many people would be able to do this, study these questions that you study. So thank you very much. The rest of us, we're doing very trivial things, but you are asking the questions about the fundamental reality of our universe. So a big appreciation from laymen like me. And yeah, you've spent your life, you dedicated your life to these questions. If there's anything you want the audience to take away from tonight, or from the title of this event, Particle Physics Today and Tomorrow, what do you want them to take away from tonight? Rebecca, you can start.
I mean, that's a very difficult question.
Yeah, it's not easy.
But I mean, I have to tell you that, I mean, since we are publicly funded, I mean, we work for you. I mean, you are our employer. So, I mean, I think you need to rethink a little bit the relationship there. Anyway, we're doing what we love, and this is pretty great. To me, I really hope that there is a tomorrow for particle physics that is even brighter than the present we have now, because, I mean, it's my favorite thing in the world. I think it's great. I really hope that everybody knows this, and I really want the people to understand, like, you guys are paying for this. Yes, ask us what we're doing. We'd love to talk about it.
Yeah, okay. So, okay, I'll readjust my question. Please justify your work to me, Anu. No.
Sorry.
No.
Yeah, so I want to stress that for the general public that there are still many open questions in fundamental physics that we really need to address. And then to add, like, my personal opinion is that I think science also makes life more meaningful, and that has value as such.
Anja.
Yeah, I think also the CERN kind of motto even is the science for peace. And this is, in the current world situation, actually in itself very important value. We do together people, the experiments, the physics studies, together with people from all corners of the world. In peaceful, we all work together regardless of background. So I think this is actually very important value also to have this kind of facility. And okay, it's for us, of course, it's good to have it at CERN. We are privileged in a sense because we have this facility at CERN. But I think we should keep this.
Yeah, you're right. Actually, in some ways, what Michelangelo said, even to a European, it sounds very reassuring that you think that way, that it doesn't really matter. In the end, it's about humanity. Yeah.
I fully share what's just been said. In addition, I can give my own way of interacting with the public, with people who don't understand why we do what we do. And in fact, I don't spend time explaining dark matter and all of these things, because in principle, you can get people excited even just by talking about gravity or thermodynamics. The physics that was known in the 1800s, electromagnetism, is not part of standard knowledge, right? So you can easily get excited people with that. I think that what we should aim at, also in our outreach and educational efforts, is to get people to understand and to learn to deal with facts, which we do every day. For us, something is right or wrong, but there is evidence, there are facts supporting the statement. And we're living in a period in which, facts are manipulated, reality is deformed, and that we have to change. And I think that trying to give people a sense of how to judge, value, and trust, not science in particular, but the scientific method is a very important message that I would like people to walk away with.
Mikko.
Yeah, for me it's answering some of these questions that I hope people are still teaching in school in 1,000 years from now. Like the Earth is round, we go around the sun, the universe is really big and the stars are actually distant suns. So hopefully they'll be talking about the universe is filled with the Higgs field that they discovered around the millennium 2000, things like this.
That's cool. Aleksi.
Yeah, I think it's pretty amazing that the number one place in the world where one can study the hardest and the most fundamental questions that there are is in the middle of Europe, and that's something that we should all be extremely proud of.
Great. Give a big round of applause to our panel tonight. They've been great. They've been amazing. And now we have about up to 12 minutes time for audience questions. Are there any eager question askers? Here, right in the front row. Go ahead, ma'am.
Thank you very much. It's not a question, it's just a remark that I wanted to do. Yes, many people think of CERN as the place for physicists to be, and it is the place for physicists to be, but they're coming from the universities, from the research institutions from all over the world. However, CERN itself is rather a lab of engineering, technology, applied science. I mean, Michelangelo here is the exception. There are only less than 3% of all the employees of CERN are physicists. And so there's a place for many people to work at CERN, starting from communications, lawyers, whatever you need. Finance,
I have a friend who's
and really spread the word out to all your technical universities. I mean, we would love to have people from Finland working at CERN from all over the specialities that are hiring at CERN. There are 250 métiers, I don't know how you say in English. How you say in English? Job titles at CERN, so there is a place really for a huge crowd of people. Yeah.
I have a friend who went to high school with me who's a fireman at CERN. So yeah. Yeah. No, he's a cool guy. He's a cool guy. Matthias, if you're out there, shout out Matthias. Any other questions from the there? Surfer guy again. All right, no, sorry for calling you that.
Okay, I have two simple questions that maybe each of the panelists can quickly answer. Is Susie dead, and do you believe in string theory?
Anyone wants to? Is that directed to anyone specifically, or do you? Everybody. Rebecca wants to answer at least one of them. I'll give that to you. There we go.
So I made a joke when I was teaching in a PhD school about Susie being dead. I use this movie when there are some friends that have a dead friend and then they carry him around in parties. This guy with the sunglasses is dead, has two people holding him, and I put Atlas and CMS, the main experiments of the LHC there. So one of the most notorious theorists of Susie noticed this, invited me to his institution for a seminar, but then the motive behind was to tell me that Susie is not dead, Susie will never die, and actually the most exciting Susie is ahead of us. So I am convinced now because I appreciate passion. So I am in the team that maybe Susie is there. That's my answer.
Who wants to answer the question about string theory? Otherwise, I'm going to have to. Yeah, Michelangelo, go ahead.
My answer is very simple. Susie's not
Let
dead,
me just
and Susie's
ChatGPT
right.
answer real quick. Sorry, Michelangelo. Yeah, sorry, I was talking over you.
Susie's not dead, and I believe in strings. So it's a very simple answer.
Fully agreed.
Good questions from the non-physics guy. Very, very, very good.
He's very much a physics guy.
I think he might be. Great. Any other questions from the audience? There's one.
So, as was mentioned, all of this research is mostly publicly funded. How do you see the public funding to research evolving in the future, and how would it affect the field?
Is that directed to anyone specific, or just the panelists? Anyone wants to on that? Oh, no.
Well, I think it's maybe getting harder and harder every year to get funding, like all these, like in Finland, we have Research Council of Finland. I think the success rates are 10% or even below. It little bit varies. And then also this European Research Council grants, they are very, very competitive. I think the number of applicants increases every year by several percent. And yeah, it's a tough situation. So hopefully politicians can realize this situation and provide more funding in the future. But of course, it's not easy. We are not living easy times at the moment.
Any questions on this side? I realize I've been neglecting you. Oh, there you go.
As I've already heard multiple times, and it was just said that actually CERN is not hiring physicists. So then, as a physicist that would like to study particle physics, then what is the smart thing to do?
Great question. Vanja.
Well, within Finland, you of course come to Helsinki Institute of Physics, or one of the other member universities of Helsinki Institute of Physics, because we are actually, most of us who work for Helsinki Institute of Physics, we are involved at CERN research, and we participate in the collaborations there. So that's the easiest route actually to come, especially you can start with the Helsinki Institute of Physics summer student program, and then from there people tend to stay on the field. But it's actually very exciting projects, typically every year. And I mean, CERN summer student positions are also another option. But many physicists kind of go more towards the applications. So maybe when you say at CERN that you don't hire physicists, it really refers to the theorists, etc. But actually many applied physicists are still physicists, but there are much more positions actually for the applied physics.
There is one important point. Physics at CERN is not done by the CERN physicists, it's done by the physicists in the community. And the key role, one of the more important roles of a physicist at CERN is somehow to steer this broad community, is to offer a training to the young physicists, for example, who come, they spend a couple of years there, they work with their hands on the experiments or the theory, and then they go back to their universities. So this is the role, and this is why we don't need to have many physicists. It's enough to have few of them just to create this environment that will allow young physicists from all over to proliferate, to learn, and then go back and have their academic career at home.
Right. Let's take one more question, if there is one. Nope, does not look like it. That's okay. We've had a wonderful evening, and I would like you to give a big round of applause to every participant on the panel, as well as the Director General of CERN, Mark Thomson, for having a great talk to us tonight. And also thank you very much to HIP for organizing this event, and I'm guessing also thank you to FCC Week, of which this is a part of this event. So let's give a round of applause. Happy birthday, HIP, 30 years old. As I'm 32 myself, I'm turning 33. So far, my 30s have been the best time of my life, so that bodes well for HIP, I'd say. Thank you all for coming. That's it for tonight. You're free to go, and if you want to stay and mingle, I'm sure that you're okay with people approaching you and coming, asking you questions if they want. Yes, confirmed. Thank you very much on my behalf. My name is Isa Krautio. It's been a pleasure to be your host tonight. Thank you, and see you. Thank you.